Okay, now we will continue with the combined loading. In fact, we have been dealing with the linear problems. So axial loading, transverse loading, torsion, bending, all are linear problems. Therefore, we can apply the superposition principle in case of combined loading. So there are problems in which we see more than one effects together. In many designs this is the case, and in fact, so what we do is we analyze each type of loading, so axial loading, bending, independently, and then sum their effects, sum up their effects, since we can apply the principle of superposition. So this is what we are going to do. We will have a better understanding after we solve some problems. So let's begin by solving the problem 820. Question is like this: determine the maximum and minimum normal stress in the bracket at section AA when the load is applied at x is equal to 300 millimeters. So we have a bracket as seen in the figure. It has a rectangular top part, and also the bottom part, the column is also rectangular. We are asked for the stress in the lower part, so in the support. Its width is 0.03 meters, so 30 millimeters. We have a 300 millimeters wide section, and then we have 150 millimeters wide section. In fact, the load is applied at 300 millimeters from the short edge, and the magnitude of the load is given as 100 kilonewtons. So what we need to do is, in fact, since we are asked for the effect, the loading state of stress in the cross section AA, so we need to transfer this force to the centroid of it, so the neutral axis, because we always assume that all the forces and moments act on the neutral axis. So this is how we do the calculation, in fact, just at the center. So we will transfer it. So let's begin by making some drawing, and so this is our bracket, in fact. We have the base here, and our cross section AA is somewhere here, and the force is acting here. This distance is given as x. In fact, the axis of the column is here, so we will transfer it to here. So let's draw it from the top view, then we will have a better understanding. It's not proportional. So this distance is, let's say, W. This distance is also W. And this is, let's say, B1. And this is B2. And then we have the force here. So W is 0.015 meters. B1 is equal to 0.2 meters. B2 is equal to 0.15 meters, and x is equal to given as 0.3 meters. So this is the distance x. So I draw cross inside a circle, which means that the force is towards the screen. Now when we transfer this force to this point, certainly there will be a point load and a moment here. So moment generated by this distance, and this will be the loading which acts on the section AA. Then we have a force, and then because of the generated moment we have MF, and this is the force F. So the direction of the MF is here, like this. So this is the neutral axis of the cross of the section AA. Anyway, so let's look at it from the side, and then we will see it much more clearly. This is where we have the A. In fact, this is the force F, and then we have this MF. So this distance is basically B1 divided by 2, and this distance is again B1 divided by 2, and this is our cross section AA. So it goes like this. Okay, so this is the loading that we have, in fact. Now what we need to do is to calculate the bending moment, MF. Bending moment MF is F. Now we will transfer the force from here, which is X, to the B1 divided by 2. Therefore the load on is equal to X minus B1 divided by 2. So force is 100 kilonewtons, X is equal to 0.3, B1 divided by 2 is 0.1, so this makes 0.2. If you multiply it with the 100, then you have 20 kilonewton meters. Okay, now we know the bending moment which acts on the cross section. Now next thing is to calculate the bending moment of inertia, because we need to calculate the stresses. In fact, this compressive force F and along with the bending moment will only generate axial stresses. And first, of course, this is tension here at the top or here, and compression here, and certainly the F force will generate in total a compressive force. But let's calculate the bending moment of inertia for this cross section. According to the neutral axis. So it is 1/12 multiplied by 2W. 2W is the width, multiplied by the height. It is b1 to the cube. Value we have is 2 10 to the power minus 5 meter to the power 4. This is the bending moment of inertia. Now let's calculate the tensile force, which is at the top. So because this moment will generate a tensile force here, and this is what I'm going to do. So in fact, sigma tensile due to the bending is equal to mf multiplied by b1 divided by 2, distance to the natural axis, divided by bending moment of inertia. So it is, if you put the values, it is 100 megapascals. So this is the stress. And in fact, for the compression, due to the maximum compressive stress because of the bending is identical, but it is negative sign. So mf E1 divided by 2 divided by I and A, then what you are going to get is minus 100 megapascals. Now we can calculate the stress due to the axial load. Sigma axial is equal to, now we have compressive force, so it's minus F divided by the area. Area is B1 multiplied by 2W. If you put the values, so .66 megapascals, and it's negative. Now we can calculate the maximum compressive. Now let's draw these two stresses. In fact, so we have a tensile stress at the top of the cross section, and then we have a compressive stress at the bottom. This is due to the bending. And then we have a compressive stress due to the axial loading, and the resultant stress is sum of the two stresses. So something like this. So we see the maximum compressive stress here and maximum tensile stress here. So the maximum compressive stress then is equal to bending stress plus the axial stress. So this is minus 100 minus 16.66, which makes minus 116.66 megapascals, and maximum tensile stress is equal to maximum tensile stress due to the bending plus the axial stress. So the maximum tensile stress is equal to maximum bending stress, tensile stress due to the bending plus the axial loading, axial stress. So this is 100 minus 16.66, which makes 83.33 megapascals. Okay, our problem is 823. The clamp is made from members AB and AC, which are pin connected at A. If it exerts a compressive force at C and B of 180 newtons, sketch the stress distribution acting over section AA. The screw EF is subjected only to a tensile force along its axis. Okay, so we have a clamp. So this clamp is exerting a force on two wooden members. The force exerted by the clamp is given 180 newtons with each tongue. Certainly, in order to apply this force, there is a screw. This screw carries only tension. So this basically means that there is a compressive force on each side of the clamp. It is pin connected at A, so there is no moment coming from the A. Fine. So first thing that we need to do is to determine the reactions forces at point A coming to the either the upper part or the lower part, and also we need to find the force which is exerted by the screw. So distance of force to the axis of the screw is given, and moreover axis of the member AC is already given. Distance to the screw, it is 30 millimeters. The cross section is given, it's a square cross section at A, it is 15 millimeters to 15 millimeters. So first thing that we need to do is to determine the forces at A and F. So let's draw the free body diagram. We can either can go from the lower arm AB or member AC. In fact, it's better to go from AC. So because we are asked for the stress at cross section A, which is on the member AC. So this is our member. We have a force. This is point C. let's say that this force is Fc. This Fc force is coming from the piece that is fixed. Then we have a tensile force on the screw. So certainly its screw will tend to elongate. As a result, it will apply some force which is in this direction at point F, and I will call it FF. In fact, we have two forces at point A. We can choose their direction arbitrarily. Fay, let's say, because I will assume that this is X and this is Y. So the horizontal coordinate is X and the vertical coordinate is Y. And then we have Fax. Now this distance is given. Let's say that this is D1 and this is D2. In fact, D1 and D2 are respectively 30 and 40 millimeters. Okay, so let's calculate the forces. We have three unknown forces, Fax, Fay and Ff. In fact, I don't have a moment at point A. So what I need to do is I can either take the moment and I will write the static equilibrium for this piece. So from static equilibrium, if we write the sum of the forces in x direction, we can easily say that Fax is equal to 0. Because there is no other force acting on the member. Now I need to calculate the Fay. Therefore, I will take the moment with respect to F. I don't want to calculate it. Sum of the moments has to be equal to 0. This basically means that Fay multiplied by D1 is equal to Fc multiplied by D2. In fact, Fc is given already. It is 180 newtons. So from here we can calculate the Fay. Fay is equal to Fc multiplied by D2 divided by Fay. D1. Okay. So Fc is 180. D2 is 0.04, D1 is 0.03. So this makes 340. Newtons. So basically, let me repeat it once more. Fay is equal to the moment generated by Fay has to be equal to the moment generated by the clamping force, that is Fc. Therefore, we can easily calculate the Fay. Fay is equal to Fc multiplied by D2 divided by D1. If you put the values, Fc is 180, D2 is 0.04, D1 is 0.03, and then we can calculate the so this is the value for D2, this is the value for D1, and then we find the force coming from the pinned connection. It is 214 newtons. Okay, we don't need to calculate the FF. In fact, this means that if we draw the normal force diagram, we can easily see that at cross section AA, so this is point A, so we have the FAY. So this is, let's say, the cross section AA, and we have the normal force. So the normal force is basically minus FAY. From here we can easily calculate it. We only have one stress component, and that's the axial load. In fact, stress there is minus FAY divided by the area. Area is, this is minus 240. Area is, so the cross section is square of the 0.015. So the value for the stress is 106 10 to the power or megapascals. Okay, our problem is 827. The column is built up by gluing the two identical boards together. If the wood has an allowable normal stress of 6 megapascals, determine the maximum allowable eccentric force P that can be applied to the column. Okay, so we have a force P which is applied on the central axis, but of course it is not acting on the neutral axis. Therefore we always assume that this force will we always assume that the forces are acting on the neutral axis, and in fact the moments. Certainly this force will generate a bending moment along with the axial force on this cross section. So what we need to do is to transfer this force to the neutral axis. And in order to do that, we need to determine the location of the neutral axis first. So if you look at the problem, so it is 75 millimeters from this edge, and certainly this is the center of the cross section, but in this direction, so it is off axis. Anyway, this will generate a moment, and we will transfer the force somewhere here first. This is what we need to do, and in fact the allowable stress, normal stress, is given, that which is 6 megapascals. It can be either compressive or tensile. Fine. So let's draw the cross section again here. Okay. Now we need to determine a reference point. Of course, I will choose the bottom line as my reference. So let's say that this is Y. And let's say that this is D1. In fact, I can define some other dimensions. So this dimension is H1, or let's say D2. This is D3. I have the location of force here. I draw it like this, so cross in a circle, which means that this is towards the cross section, so through the inside. So we have D3. Let's say that this is D4. We have here D5, and this distance is D6. So certainly D1 is equal to 0.15 meters. D2 is equal to 0.25. D3 is equal to 0.15 again. D4 is equal to 0.3. D5 is equal to 0.075, and D6 is equal to 0.05, and the units are meters. This is 0.075. Okay, so now first thing that we need to do is to determine the location of the neutral axis. Of course, neutral axis is somewhere here. In fact, it is sum of the moments, first moment of the areas divided by the total area. So y bar is the location of the neutral axis. In fact, we have two subsections, sub-areas. So one is this vertical one, and the other one is the horizontal one. Let's begin from this one. Centroid is located at D2 divided by 2, and the area is D2 multiplied by D1. Now the horizontal part, the centroid is located at D2 plus D3 divided by 2. So this is the first moment of the area of the vertical one, D2 divided by 2. This is the area, D2 multiplied by D1, and the centroid of the vertical piece is located at D2 plus D3 divided by 2, and the area is D3 multiplied by D4. Total area is d2 multiplied by d1 plus d3 multiplied by d4. So the result is 0.234 meters. So this is the location of the neutral axis. Now next thing is to calculate the bending moment of inertia, because this force will generate a bending moment in fact. So let's So we will calculate the bending moment of inertia with respect to the neutral axis. In fact, again, we have two areas. One is the vertical one, the other one is the horizontal one, and we will calculate their bending moment of inertia with respect to the neutral axis. First, the vertical one, it is 1/12 d1 multiplied by d2 to the cube. Then we will shift it to the neutral axis. It is the area multiplied by distance between the centroids, distance between the neutral axis and the centroid of the area d1, d2. So that is d2 divided by 2 minus y bar square. Now we will calculate the moment of the area of the horizontal one. That is 1/12 d4 multiplied by d3 to the cube plus d4 multiplied by d3, and its centroid is located at d2 plus d3 divided by 2 minus y bar square. So this is the moment of inertia of the vertical area with respect to its central axis, and then we shift it. It is the area multiplied by distance of its centroid, central axis to the neutral axis. So the axis of the vertical area is located at d2 plus d3 divided by 2. Okay, so this is the moment of inertia, bending moment of inertia. The value that we have is 1.097 10 to the power minus 3 meter to the power 4. So this is the bending moment of inertia. Now what we need to do is to calculate the bending moment. In fact, let me draw the cross section again. We are given the force here. In fact, neutral axis is somewhere here. So this force has to be transferred here. And then this will generate a force, or let's draw it here. That's better maybe, in order to avoid the confusion. So we have a force plus bending moment generated by this force. So this is the force P. Now we can calculate the bending moment. Bending moment is equal to force multiplied by y bar minus d6. So this is the distance, d6 is the distance to the reference point or edge, and this is the distance location of the centroid. So this distance is the moment arm. In fact, we don't know the magnitude of the P, so let's leave it like this. But in fact, we can easily, of course, we can easily say that this is the moment. Since this force will generate a compressive stress, because it is towards the cross section, and this will generate a tension here and compression at this point. Obviously, I can say that in this type of loading, I see the maximum stress here, because this will generate a compressive axial normal force, normal stress, and this will generate a compressive stress here. Or let's draw it. So basically, if we look at from the side, so now we have this force P. In fact, this is the neutral axis, and then we have this bending moment. So certainly force P will generate a uniform stress distribution, which is compressive, and of course, and B will generate such kind of a stress distribution. and the result of this two stresses will in fact something like this. Obviously, by means of absolute value, I will see the sigma max here. So let's calculate the stresses for this point then. First, I will calculate the bending moment, bending stresses. So bending stress for this point is MB multiplied by distance of that point to the neutral axis, that is y bar, divided by INA. Of course, I have the negative sign because it is compressive. So let's put the value for that. So that is minus P y bar minus D6 multiplied by y bar divided by INA. So this is the stress due to the bending. Now let's calculate the stress due to the axial loading, and in fact let's call it sigma A. So that is minus P divided by the area, or that is minus P D1 multiplied by D2 plus D3 multiplied by D4. So sigma max, absolute value of the sigma max, is equal to P multiplied by y bar minus D6 divided by y bar divided by INA plus P divided by D1 multiplied by D2 plus D3 multiplied by D4. And in fact, in the limiting case, this has to be equal to allowable shear stress, allowable normal stress, sorry, because these are normal stresses. So in any case, in the extreme case, this is what we have, and from here we can calculate the P. P is equal to then sigma allowable multiplied by INA multiplied by D1 multiplied by D2 plus D3 multiplied by D4 divided by y bar minus d6 multiplied by y bar multiplied by d1 multiplied by d2 plus d3 multiplied by d4 plus I and A. So this is the expression for the therefore the value for the P is 116.791 kilonewtons. Okay, our problem is 834. The control lever is subjected to a horizontal force of 90 newtons on the handle. Determine the state of stress at points E and F. Sketch the results on differential elements located at each of these points. The assembly is pin connected at C and attached to a cable at D. So we have a lever. We apply a load of 90 newtons and it's pin connected at C, which means that there is no reaction moment at C. So we only have reaction forces at point C, and then it's connected to a cable from point D, and the other end of the cable is fixed. So certainly when you apply a force in this direction, in fact the point D will go in the upward direction. As a result, the cable will be in tension, and we are asked for the state of stress at point F. F is on the neutral axis of this cross section, which is seen in the figure. It's a rectangular cross section, in fact, and so the other point that we are asked is the point E. So point E is on the vertex, so it is a square cross section on the handle. Okay, so first thing that we need to do is to determine the reaction forces at C and the force exerted by the cable. So point D, in fact, if we look at the problem clearly, we see that we only need to calculate the force exerted by the cable. So in order to calculate the internal forces and moments in this cross section, and it is the same for the point E, in fact, so we don't need to calculate the reaction forces at point C, because we can make a cut from here, and then from the equilibrium conditions we can easily determine the internal moments and forces, and then we can calculate the state of stress at these cross sections. Okay, so let's begin by drawing the free body diagram of the handle. We will make a simplified sketch. So this is our handle. In fact, we have a force in this direction, So let's say that this is F, and then we have another force here. So let's say it is perpendicular because it's applied by the cable. It is Ft, and certainly we have two forces at point C. This is Fcy, and let's say that this is Fcx. If we choose the coordinate system x and y. Of course, we are asked for the stresses here, so this is point F. In order to make it more clear, let's say that this external force is FH, okay, and this is our point F, and then we have the point E here. So let's define some variables, in fact. So this is D1, and then we have another dimension here. So let's say that this is D2. So from the applied force to the handle, and then we have this distance, that is D3, and then this is D4. So these are the forces. Okay, so now, in fact, I don't need to calculate the forces at point C, therefore I will take the moment with respect to point C, and in fact some of the forces acting on the system has to be zero for static equilibrium. Therefore I will write it so. I will write the sum of the forces with respect to point C. Now from here I can easily say that moment generated by the force coming from the cable Fd, and the load arm is D3 plus D4, and this is equal to, because they will try to rotate this handle in opposite directions, so Fd and Fh. So Fh is in clockwise direction and Fd will tend to rotate it in the counterclockwise direction, Fh multiplied by D2. In the meantime, let's put the values for the various dimensions. So D1 is equal to 0.05 meters, D2 is equal to 0.125, D3 is equal to 0.02, and D4 is equal to 0.045. So from here we can calculate the Fd. Fd is equal to Fh multiplied by D2 divided by D3 multiplied by plus d4. So Fh is 90. D2 is 0.125. D3 is 0.02. And D4 is 0.045. The value is, if you make the calculation, the value is 173.077 newtons. So Fh is already known to be 90 newtons. Okay, now we know the forces. Now we can either calculate the stresses for point F and E. So let's begin by calculating the stress for point F. This is Fh. Now we are here, and certainly what we are going to do is we have the internal force here, let's say V and Mf. Of course we have the normal force Nf for this point. Now we choose another coordinate system, let's say x prime and y prime, which is parallel to the load arm. In order to make the things clear, simple. So these are the forces, internal moments and forces. Certainly Nf is 0, so again sum of the forces has to be 0. From here we can say that Nf is 0, so there is no normal force at point F. Vf is the shear, so that is minus Fh, and Mf is equal to, so remember that this distance is already known, it is given a priori, it is d3, so this is where we make the cut. So Mf is equal to, sorry, this is not Fh, this is Ft. Okay, minus Ft multiplied by d3. So the value is minus, so Mf has the value of minus 3.461 Newton meters. And FD is already known, so I will not write it again. Now, as we see, we have two external loadings. Therefore, we have normal stresses due to the bending, MF, and certainly we have shear force, which will cause a shear stress. So, first thing that we need to do is to calculate the bending moment of inertia. In fact, we will need to in order to calculate the shear stress, and bending moment, we certainly need to calculate the bending moment of inertia. So at point F, the cross section is something like this, very thin. This is the neutral axis. Here, let's say that the dimension is d5 and it has a height and this is, let's say, d6 here. So d5 is equal to 6 10 to the power minus 3 meters, and d6 is equal to 12 10 to the power minus 3 meters. Okay, now we can calculate the bending moment of inertia for this cross section. In fact, we can write the loading. So, but okay, doesn't matter. Let's write the bending moment of inertia for this cross section. Let's say that this is IF. So, in the meantime, we are asked for the stress at this point. So, for this cross section, it is simple. The neutral axis is just known. It is 1/12 d5 to d6 to the power cube. This is the location of the neutral axis, in fact. So the bending moment of inertia for the cross section is 6.912 10 to the power minus 9 meter to the power 4. Now we need to calculate the first moment of the area above the neutral axis, because we are asked for the shear stress, in fact. So we need the shear stress value for this particular cross section, and so QF is equal to, now the center is located at d6 divided by 2 multiplied by the area. It is d5 multiplied by d6. If you put the values, it is 4.32 10 to the power minus 7 meter to the cube. Now we know the first moment of the area, bending moment of inertia, and shear stress. So certainly we can calculate the shear stress at point F. So for point F, it is minus VF multiplied by the QF divided by bending moment of inertia at this cross section multiplied by the thickness, and the thickness is d5. So it is, the value is minus 1.802 megapascals. So this is the stress. So minus sign comes because obviously the stress on the differential element is like this. So this is the front face that we calculated. Now we are asked for the we have also bending moment, but certainly we are asked for the bending stresses at point F, which is located just on the neutral axis, and we know that on the neutral axis the stress is 0, at least bending stresses are 0, so we can easily say that the normal stress at point F is 0. So we don't need to calculate it. Okay, now this is the case for point F. Now let's continue with the point E. Okay, so for point E, we have the force which is applied to the handle, and we have this distance, let's say d1, let's say we have the bending moment ME, and we have shear stress at point E, shear force, sorry, and then we have the normal force in E. Okay, now obviously we have some of the forces has to be equal to 0, which gives us that NE is equal to 0, and from here we can calculate the shear force at point E. So the shear force at point E is equal to FH, and that's equal to 90 newtons. Now obviously ME is equal to minus FE multiplied by the D1. Or in order to be consistent with the previous definitions, let's take the bending moment in the opposite direction. So this becomes ME is equal to then FH multiplied by D1. The value is then 4.5 Newton meters. Now if you look at this particular cross section, we see that it's a square cross section, and in fact we are asked for the shear stress at point E. Now the point for point E, it is just on the surface, and obviously we can say that the shear stress is 0 for this point. Therefore we don't need to calculate any in fact Q value is 0 for this particular point, and as a result the shear stress is 0. Therefore we can say that TE is 0, but of course there is a bending moment, and this bending moment shall be calculated, and for this purpose we need to calculate the bending moment of inertia. So shear stress for point E is obviously 0. We have tiny square cross section with the edge length of 7.5 millimeters. So let's say that this is D7 and this is D7 as well. So D7 is 7.5 10 to the power minus 3 meters. So let's calculate the bending moment of inertia for this cross section. IE is 1 over 12 D7 to the power 4. So the value is 2.636 10 to the power minus 10 meter to the power 4. Now of course E is located here, so this is where our neutral axis is for this tiny cross section. So it is just located at the center, so we can calculate the normal stress at point E. So that is basically compressive because of the it is tensile. Okay, so it is plus ME. Distance to the neutral axis is d7 divided by 2 divided by bending moment of inertia of the cross section. And the result is 64 megapascals stress. Of course, if we draw the stress for this particular location, we have only normal stresses, and we don't have any other stress component acting on the differential element. Okay, our problem is 836. Now the drill is jammed in the wall and is subjected to the torque and force shown. Determine the state of the stress at point A on the cross section of the drill bit at section AA. Okay, so we have a drill and the drill bit is jammed. There is 20 Newton meters torque is applied to the drill bit, and 150 newtons of force applied by someone to the drill itself, handle of the drill. The coordinate system is already given to us, so the y is the vertical and x is the horizontal, but towards the left. In fact, z coordinate is perpendicular to the boat and towards us from the surface of the screen or plane that we are interested in. The drill bit is assumed to be perfectly circular, the radius is given. So this is our problem. In fact, we need to determine the internal forces and moments at section AA. In order to do that, we will first determine the reaction forces coming from the wall to the drill bit, and it will be fixed to the wall. We will, as is seen from the figure. So let's draw the free body diagram of the problem. So this is our drill. We have a force F. Now this is our point A, and in fact we have a moment T, let's say, on the drill bit. Of course this is a little bit idealized. So next thing is we have a support reaction in both directions, FAY, and also in positive X direction, FAX. I assume that the forces are all positive. And then I have a support reaction MA, moment, bending moment, and second we should have a support reaction to the torque, which is TA. So MA is in Z direction by means of if we from vector point of view. Okay, now let's write the sum of the forces. In fact, we don't have any forces in Z direction. Sum of the forces in X direction is equal to 0. So this is FAX plus four over 5 F, and that has to be equal to 0. In the meantime, the value of the F is already known, so it is 150. And okay, so FAX is equal to minus 4 over 5 F, which makes minus 120 newtons. Now let's continue. Sum of the forces in Y direction has to be equal to 0. Now we have FAY plus 3 over 5 F, that's equal to 0. From here FAY is equal to minus 90. Now let's continue the moments in X direction. So this is in X direction we have only torques. Sum of the moments in X direction is equal to 0. Now in X direction we have the torque applied by the drill and reaction coming from the wall. We choose the both of them in the same direction, so TA is equal to minus T, and that is equal to minus 20 Newton meters. Now we don't have any moment around Z-axis, so we only have the moment around we don't have any moment around Y-axis. We only have moment in Z-axis, so sum of the moments in Z direction has to be equal to 0. Now so remember that the positive Z direction is always towards us, so MA is positive the reaction moment on the wall, and this has to be compensated by the force generated by the handle. So that is F. Let's define some dimensions here, maybe that's better. So we have two dimensions. So let's say this height is d1, and this distance is d2. So d1 is 0.125 meters and d2 is 0.4 meters, and T is already known. T is also 20 Newton meters. So let's write it so. Okay, now we can calculate the MA. So in the y direction, force applied to the handle generates a moment. So it is 3.5 F multiplied by d2, and force in the x direction applied to the handle will generate a negative moment in this case. So that is minus 4/5 F multiplied by d1, and this is equal to 0. Now from here we can calculate the MA. MA is equal to 4/5 F multiplied by d1 minus 3/5 F multiplied by d2. So the moment is minus 21. Bending moment is minus 21 Newton meters. Now what we are going to do is, we know the support reactions. In fact, let's find the internal forces and moments. Now we have the cross section. You make an arbitrary cut somewhere on the drill bit. This is our point A. So I will not write it, but let me draw the forces now. We have FAX, TA, MA, FAY. We have the shear force V internal. We have the bending moment MI, and then we have the normal force NI, and certainly at this particular cross location we have the internal torque TI. Now obviously we can calculate the values. It's quite simple and straightforward. So VI is equal to FAY from the equilibrium conditions. So NI is equal to FAX, TI is equal to TA, and MI is equal to minus MA. Plus FAY multiplied by X. So this distance is X. In fact, we are looking for the position. We need to calculate the stresses at cross section AA, and for this point this is 0, FAY, because X is equal to 0. Okay, now we know the internal forces and moments. So let's write the values. VI is equal to FAY. FAY is minus 90 newtons, and then next thing is NI. NI is equal to FAX. FAX is equal to minus 120 newtons. TI is equal to TA, and TA is equal to minus 20. Now MI is equal to minus MA. MA is minus 21, so it is equal to 21 Newton meters. Okay, now let's draw the cross section. So this is our cross section. For this cross section we have the radius r. So it is symmetric. Neutral axis is just located, passes from the center. So r is 5 millimeters, 510 to the power minus 3 meters. And we are asked for the state of stress at point A. So at this point, so we need to calculate the shear stress. In fact, within this cross section we have two shear stresses. One is due to the torsion, and the other one is due to the transverse force, external force. And in fact we are asked for the shear stress at point A. So for point A, first moment of the area Q A is equal to 0. So stress due to the transverse force is equal to 0. We don't need to calculate the moment of inertia or other things for this point. Now the second thing is we have normal stresses. In fact, we have two normal stresses. One is due to the bending and the other one is due to the axial loading. So therefore we need to calculate the bending moment of inertia for this cross section. So bending moment of inertia I bending is equal to P r to the power 4 divided by 4. The value that we have is, for the bending moment of inertia, it is 908 10 to the power minus 10. Meter to the power 4. Okay, this is the bending moment of inertia, but in fact we need to calculate the rotational moment of inertia for the cross section. Rotational moment of inertia for the circle is P r to the power 4 divided by 2. If you put the values, what you are going to get is .817 10 to the power minus 10 meter to the power 4. Now we can calculate the shear stress due to the torsion. So shear stress due to the torsion is equal to, at point A, Ti multiplied by distance from the center, it is r, divided by IR. So the value is 101.859 megapascals. So this is the shear stress. Well, by the way, it's negative, huh? But it is just a sign convention because it is just about the direction. Okay, so next thing is normal stresses. Now we have a normal stress due to the axial loading. So that is Ni divided by P r square area. So the value is, for the stress, it is minus 527 megapascals. Now the next thing is stress due to the bending. Now stress due to bending is equal to minus mi so it is minus mi multiplied by r divided by I bending. So the value is minus 21.39 megapascals. So the stress in the normal direction for point A is equal to sigma n plus sigma b, and the value is minus 21.543 megapascals for this cross section. So as a result, we have the total normal stress which is equal to minus 21.543 megapascals for this cross section, and we only have shear stress due to the torsion, and it is 100. It's around 100 megapascals for the cross section. Okay, our problem is 839. The frame supports the distributed load shown. Determine the state of stress acting at point E. Show the results on a differential element at this point. So we have a frame, we have a distributed load acting on it. So linearly increasing one up to 4 kilonewtons per meter, and then it decreases to 0 at point B. There is another member which doesn't have any load on it, and we are asked for the state of stress. It has a rectangular cross section. The structures, the members have a rectangular cross section, and in fact we are asked for the state of stress at point E. So let's write the forces acting on each member first. Let's draw the free body diagram of them. This will be the first step. In fact, we need to determine the support reactions in order to find the state of stress at point E. Okay. So this is our first member. So here it increases linearly up to a point, and then it decreases. Sorry, it's not proportional. So this is point A, and this is point B. this point is D in fact, and we are asked for the state of stress at point E. Now when we look at the problem, certainly the BC member carries only load along its direction. So I will just choose a direction for it. So we don't know whether it's positive or negative, but certainly I assume that the member BC applies a force in this direction to member AB, and then of course at A we have two forces. If we choose the X as the horizontal and Y as the vertical coordinate system, so at point A we have two forces, FAY and FAX, and this is the force at B. Certainly the slope is already known. So this is 3, this is 4, and this is 5. So the angle is already known, let's say theta. So in fact sine theta is 3/5, and cosine theta is 4/5. Okay, so let's take the moment with respect to, by the way, this is the distributed load that we have, and let's write the distance in fact. So let's denote some variables for simplicity. In fact, from A to E it is L1, then we have L2, and in fact this distance is L3. And we have the magnitude W0. So W0 is 4 kilonewtons per meter. L1 is 1.5 meters, L2 is 1.5 meters, and L3 is equal to 3 meters. Okay, so first thing is to determine the support reactions, and in order to determine the internal forces, therefore we need to, what we are going to do is, first we will calculate the moment with respect to point A. So sum of the moments for the static equilibrium has to be 0 with respect to A. This will eliminate the contribution of the support reactions at point A, and from here we will have FB multiplied by 3/5 multiplied by L1 plus L2 plus L3. This is the moment generated by the force at point B. then we need to calculate the contribution of the distributed load. In fact, this distributed load have two parts. One we have here, or it is certainly, it just acts at the center because it is symmetric both hand side. I didn't draw it properly, but so the area under the triangle is W0 multiplied by the area divided by 2. So the resultant force of the distributed load is W0 L1 plus L2 plus L3 divided by 2. This is the resultant force. And then the moment arm, again L1 plus L2 plus L3 plus, or L1 plus L2, let's say. Load arm, because this is the distance of D from point A. So this is equal to 0. By the way, this is minus. This has to be minus, because the force and force generated by the distributed load and the force generated by the FB, or moment generated by FB and moment generated by the distributed force causes have reverse direction, has opposite direction. So this is what we have. In fact, this will cancel this expression, and from here we can calculate the FB. So FB is equal to W0 L1 plus L2 multiplied by 5/6. So the value is 10 kilonewtons. This is the magnitude of FB. Now we need to calculate the support reactions at A. We don't have any moment there. We have only two forces. So in fact we can calculate them from static equilibrium. So sum of the forces in each direction has to be equal to 0. So in each direction we have FAX minus 4/5 FB, and that's equal to 0. So FAX can be calculated from here as 8 kilonewtons. Now in y direction, sum of the forces in y direction has to be equal to 0. Now this gives us FAY. FAY is equal to W0 L1 plus L2 plus L3 divided by 2 minus 3 over 5 So Fy, let me repeat it again. Fy is equal to W0 multiplied by L1 plus L2 plus L3 divided by 2. This is the resultant force generated by the distributed load. Then we need to subtract the contribution of the force that comes from the Fb. So this is 3 over 5 Fb. And the result is 6 kilonewtons for Fy. Okay, now we have found the stresses. Now, in fact, what we need to do is to determine the internal forces and moments which generates the stress. So what we are going to do is we will cut at an arbitrary location between A and B, and we will write the expressions for the shear force, bending moment, and normal force. So this is Fay. We have Fax. Then we have the W here. Now the W is equal to W0 divided by L1 plus L2 multiplied by x at an arbitrary location. So this distance is x in the meantime. Now we have the normal force V, N, we have the shear force N, and we have the bending moment M for this particular location. So let's calculate the forces. So in each direction we will write the force equilibrium for this configuration. So first let us begin by the vertical component of the force. In fact, we have Fay. Then we have the resultant force of the distributed load. So this is minus W0 L1 plus L2 multiplied by x multiplied by x divided by 2. So this is the resultant force of the distributed load when you have the width of x. And then we have minus V. So from here we can calculate the V. V is equal to W0 x squared divided by 2 L1 plus L2 minus FAY. Now let's write the horizontal component of the force. So components of the force, Fax plus N is equal to 0. And from here we can calculate the N as minus Fax. Now the final expression for us is the bending moment. Now we will calculate the moment, which is, we can calculate the moment with respect to any point, but we prefer to calculate the moment with respect to the cut. So therefore we will not there will not be any contribution coming from the shear force and Fax, so we only have the contributions coming from the Fay and moment generated by this distributed load. Certainly the moment generated by this distributed load is acting at a distance of x divided by 3. We have the moment, and in the same direction the distributed load generates a moment, and the moment force is W0 x square divided by 2 L1 plus L2 multiplied by x divided by 3, and then the moment generated by the Fay, it generates a moment in the opposite direction to the M. So moment generated by the Fay is clockwise. Fay multiplied by x, and that's equal to 0. So M is equal to Fay multiplied by x minus W0 x cubed divided by 6 L1 plus L2. This is the moments and forces as a function of x. So from here we can easily calculate the values acting at the cross section E. So VE is equal to Vx equal to L1 and that's equal to W0 L1 square divided by 2 L1 plus L2 minus Fay the value is then minus 4.5 kilonewtons, and we certainly have the N is equal to minus Fax so Ne is and x equal to L1, and that is equal to minus 8 Now the bending moment at E is equal to m x equal to L1, and that's equal to FAY multiplied by L1 minus W0 L1 cube divided by 6 L1 plus L2. So the value of the ME is then 8.25 kilonewton meters. Okay, now we have found the values for the cross section. Now we have a square cross section, rectangular cross section, sorry, and we are asked for the state of the stress at point E. In fact, the state of the stress at point E and D are the same, but we are going to calculate it for point E, so it doesn't change something for us. Well, it will change, in fact, due to the bending moment and bending stresses, because stresses that the directions of the forces, stresses at point D and E are different. Okay. Now let's draw our cross section. We have a rectangular cross section. Certainly the neutral axis is just at the center. And we are asked for the point E here. Let's say that this is B. B is given as 50 millimeters. It is 0.05. Then we have another dimension, H. So H is equal to 100 millimeters. So it is 0.1 meters. And distance of E is, let's say, DE, and that's given as, from the figure, it's obviously 30 millimeters, it's 0.03 meters. Okay, so first thing that we need to do is we need to calculate that we don't have any torque applied to the cross section, so we don't need to calculate the rotational moment of inertia, but in fact we have shear force and bending moment. Therefore we need to calculate the bending moment of inertia for the cross section. So let's do it first, and then we will calculate the first moment of the area. So bending moment of the inertia with respect to the natural axis is 1 over 12 b h cube So the value we have is 4.166 10 to the power minus 6 meter to the power 4. Okay, now let's calculate the first moment of the area for Q for point E. In fact, first, the location of the centroid. Centroid is located as let's define in another dimension here. So maybe it will make another simplification for us. So DE, and let's say that this is HE, and HE is equal to 0.02 meters in fact. So it is H minus HE divided by 2 minus H divided by 2. So this is the distance to the neutral axis. Sorry, one more correction. So this is plus HE in fact. So let's write it here again. So H minus HE divided by 2 plus HE minus H divided by 2. Okay, and the area is B multiplied by H minus HE. So in other words, Q is equal to HE divided by 2 multiplied by B multiplied by H minus HE. So the value is 10 to the power minus 5 meter to the cube. Now we have the Q values. In fact, we can calculate the stresses. First, let us begin by the shear. We have only shear stress due to the transverse load. It is VE shear force multiplied by the first moment of the area divided by bending moment of inertia multiplied by the width at that point. The value is minus 0.864 megapascals for the stress, shear stress at point E. Now we have two stresses. One is due to the bending and the other one is due to the axial loading. Let's calculate the stress due to the axial loading. So sigma n is equal to NE divided by the area. Area is B multiplied by H. So it is minus 1.6 megapascals. Then we have the stress due to the bending. That is minus ME multiplied by the location of the E, distance to the centroid, that is minus DE, in fact, divided by IE. So the value is so again, let me repeat it once more. So we have the bending moment ME minus DE, because we put the axis in bending on the neutral axis. So this is the distance to the neutral axis. It is on the negative side. So minus DE divided by bending moment of inertia. And from here what you obtain is 59.4 megapascals. Now the stress in the normal direction is equal to normal stress plus normal stress, because axial, normal stress due to the axial loading, normal stress due to the bending, and then what we have is obviously 57.8 megapascals. Now we are asked for the drawing of the shear stress on a differential element. So if this is our differential element, so this is the front face. So in fact, if you want to show the shear stress on the differential element, we have sigma here. It is tensile, and in fact we have the negative shear, so these are the shear stresses. On the differential element. Our last problem in this chapter is 8.54. The 25mm diameter rod is subjected to the loads shown. Determine the state of stress at point B and show the results on a differential element located at this point. So we have a rod which is L-shaped, bended. In fact, it is fixed to the wall at point C. And we have a point load applied to the tip of this rod, and certainly we are asked for the state of stress for point B. Well, there is a coordinate system attached to the cross section, so it's already given a priori. The distance between the tip to the cross section is given in x-axis and in z-axis, so it is in the xz plane basically. Now what we need to do is, first we have to calculate the internal forces and moments acting on the cross section. So at this cross section, therefore we will make a cut from this cross section, and then we will put the internal moments and internal forces on the surface. Then we will apply we will check. So in any case, this piece has to satisfy the static equilibrium conditions, and therefore we can easily calculate the forces. Okay, so now let's draw the simple with the rod, and so we have the rod here, and let's say that we have two ends. This is D, and we have the cross section here. So in fact, let's say that this is where our point B is. This dimension is given a priori. Let's say that this is D1, and then we have the second one. This is D2. Now at point B, the coordinate system is already given. This is X, this is Z, and we have the Y coordinate perpendicular to it. So let me show it like this. Okay, now D1 is already given. It is 0.075. D2 is 0.2. Now we have the internal moments acting at the cut and internal force. And certainly we have an F. At the free end. Now F can be written easily because the components of the force is already given. We will write it in Cartesian coordinate. It's minus 350I minus 375 J vector, and then plus 450 K vector. So these are this is the force of F acting on the free end. Now this system has to be in static equilibrium. So sum of the forces has to be equal to 0, which means that F plus internal forces has to be equal to 0, and from here internal force is equal to minus F, and that's equal to 350 I vector plus 375 J vector minus 450 K vector in newtons. Now we need to calculate the moments. Some of the some of the moments has to be equal to 0. We will take the moment with respect to the origin of the coordinate. This will eliminate the moment generated by the internal forces. So therefore we have a moment, internal moment, and the other one is the moment generated by this force, and in fact this is the load arm multiplied by the force. So this is R dB, so position of vector of B with respect to D, vector product F plus internal moment. This has to be equal to 0. Therefore internal moment is equal to minus R dV vector product F. Sorry, let's write it here again. Emint. It's confused. Emint minus R dV vector product F. So we know the RdB. RdB is equal to, this is minus, so this is minus d2 I vector plus d1 K vector. And then vector multiplication of it with the force, x component of the force plus y component of the force plus z component of the force. Now, if you do the calculations, if you put the values and do the calculations, what you are going to get for the internal moment is minus 28.125 I vector minus 63.75 J vector minus 75 K vector, and the unit is Newton meters. So we have we found the internal moments and forces. Now there are certainly torques. So in fact the X component of this force, internal force, will generate axial loading, and Y and Z component of the force will generate the shear force. So therefore let's write the forces individually. So we have Nx, in fact that's 350 newtons. We have Vy is 375 newtons, and Vz is actually minus 450 newtons. Now we have the torque. So X component will generate torsion, X component of the moment, which is minus 28.125 Newton meters. We have Y component of the moment, that is the bending moment, My, that is minus 63.75 Newton meters, and we have the bending moment Z, Mz, that is minus 75 Newton meters. Well, now, okay, we need to calculate the normal force, shear force. We have just calculated the shear forces and forces, and then torsion, the torque that is applied to the cross section, and bending moments. Now, in order to calculate the bending stresses, we need to calculate the bending moments of inertia. Since we have a circular cross section, so let's draw the cross section here, in fact. This is our cross section. Sorry for the bad drawing. Now in both axes, the system is symmetric, so obviously we don't need to calculate the location of the neutral axis. And so we just will calculate the shear forces. So just a second. So let's say that this is z-axis, this is y-axis, and this is where the point B is located. So we are asked for the stresses for point B. In fact, the shear force which acts on the z-axis will not generate any shear stress at this point. So we have only two shear stresses. One is due to the torque and the other one is due to the shear force in y direction. So let's calculate the shear forces. So Vy is already given in this direction, so this is positive, like this. And we have the torque x, it is negative. So this means that torque is clockwise. Okay, so let's calculate the stresses. In order to calculate the shear stress, we need to calculate the bending moment of inertia, and so it can be any bending moment of inertia. So it can be Iz, and simply Iz is equal to Iy. Now it is P r to the power 4 divided by 4. This is the bending moment of inertia for the cross section. In fact, the value is, so R is 12.5 millimeters. So it is 12.5 10 to the power minus 3 to the power 4 divided by 4, and if you put the values, what you have is then 1.917 10 to the power minus 8 meter to the power 4. So these are the bending moments of inertia in both axes. Now we need to calculate the rotational moment of inertia. That is P r to the power 4 divided by 2 . The value is 3.834 10 to the power minus 8 meter to the power 4. Okay, so these are the rotational moments of inertia and bending moment of inertia. So Now next is we need to calculate the Q value. So we have only, as we said, stress contributed in the y direction, because the stress in z direction will not contribute, because Q is here 0 automatically. In z direction, therefore we will calculate the Q value in y direction. So first moment of the area, and it is in fact so in y direction we have positive, so it is in this direction, so we can calculate either of the halves. So the area above the circle multiplied by its centroid will give us the first moment. In fact, this distance is already known from the geometry, so that is (4r) divided by 3p. Okay, now let's calculate the moment of the area. So it is y bar multiplied by the area, that is 4 divided by 3, r divided by p, p r square divided by 2. So the value is 1.302 10 to the power minus 6 meter to the cube. Now we can calculate the shear stress, because or let's calculate the area as well. Area is P r square it is 4.908 10 to the power minus 4 meter square. Okay, now we have found all the values. Let's begin by calculating the shear. So the shear stress for this particular location is, we have shear caused by the Vy, so Vy multiplied by Qy divided by Iz multiplied by the thickness. Thickness is 2r at that location. Now certainly the shear stress is in positive direction. Then we have the shear generated by the torque. Now I will use the absolute values. So I know that torque is in negative x direction. but this will generate the same torque, or I can put the minus sign here in order to be compatible, but in fact I will not do that. So Tx multiplied by R divided by rotational moment of inertia. So this is the shear stress. I can put the values. If you put the values, the value that we have is 10.185 megapascals. So this is the shear stress at this point, and it is positive in y direction. So it is tau xy. Now let's calculate the normal stress. Again, I will draw the cross section again here in order to make the things clear. So this is my z-axis, and I have my y-axis here. Now certainly the moment is acting in this direction around z-axis, and my is also negative, so my is like this. So both are, sorry, this is around z-axis, yes, this is mz, and this is my. Now of course, when you have a moment like this, at point B, this will generate a compressive force because of the direction, and mz will not generate any stress at this point. So we have only stress due to the my and normal force. Therefore sigma is equal to nx divided by the area. Okay, and my multiplied by r and divided by IY. So this is the normal stress. If you put the values, the value that you are going to have is minus .84 megapascals. So this is the answer of the question. So certainly the stress on a differential element at point B is, this is tau. If this is x, this is y, then we have this stress sigma. This is tau, this is tau, and this is sigma. And this is also tau.